Welcome back, students. We are going to be starting a new unit now. This is Unit 19. We're going to talk about nuclear chemistry. I think that up till now, we have studied about all of the processes that involve electrons here, electrons there. It is time to give the nucleus and the neutrons and protons equal opportunity. Okay, so we're calling this Unit 19. This is in keeping with the sequence that we established since Chem 1A. Here are some of the topics that we're going to be discussing. We're going to talk about the atomic nucleus and radioactivity. Then we're going to talk about nuclear stability and nuclear reactions, and especially learn how to balance nuclear equations and deal with energy aspects of these types of transactions. And then we'll try to look at some applications, particularly of radioisotopes and nuclear energy. Let's go back to something we learned back in Chem 1A, and that is, in the beginnings of the 20th century, we had a picture of the atom that was based mainly on the model of Rutherford as a result of their experiments. And that was that the atom, as small as it was, had an even smaller nucleus consisting of protons and neutrons, and then electrons spread out in a comparatively vast amount of space. For comparative purposes, realize that an average atomic radius would be about 100 picometers, whereas the nucleus by itself would have a radius of about 5 thousandths, or 5 times 10 to the negative 3 picometers. So yes, these are very, very small numbers. Atoms are incredibly small particles, but if we could kind of like blow them up into something that makes sense to us, we would say that if the atom is the Rose Bowl, then the nucleus is like a marble on the 50-yard line, just to give us a sense of the dimensions of these subatomic particles. In Chem 1A, we also learned some definitions. Number one, the atomic number, which we use to represent with the letter uppercase or capital Z, and this is the number of protons in the nucleus. The other important number we defined was the mass number, capital A, which represents the number of protons plus the number of neutrons, or the atomic number plus the neutrons. So if we have a particular atom and we know the atomic number, which is essentially the identity of the element, and we know the mass number, we can subtract A minus Z to give us the number of neutrons in that particular atom. We use this format to represent these atoms, where X here stands for the element symbol, which we find in the periodic table. A would be the mass number placed on the upper left, and then Z, the atomic number, would be placed on the bottom left. All right, and some definitions. We know that isotopes are atoms with the same atomic number, in other words, the same value of Z, but a different neutron number, and therefore a different mass number, A. Now, in nuclear chemistry, we're going to use a bit of a different terminology, because we're not going to be dealing many times with large samples of measurable amounts. We're going to be measuring more the activity of these things and refer to them almost as if we were dealing with individual particles. And so we're going to say that subatomic particles, like protons and neutrons, of which the nucleus is made, we're going to call them nucleons. And then a nuclide is going to be an atom with a particular number of protons and neutrons. In other words, a particular value of Z and of A. So a nuclide is sort of like the atom of what we normally call an isotope. Now, here comes the interesting part, radioactivity. Let's start out by defining what we mean by radiation. So radiation is energy that comes from a source and travels through matter or space. We're going to classify two types of radiation, electromagnetic and particulate. Electromagnetic would be anything in the electromagnetic spectrum that includes light, gamma rays, X-rays. Now, particulate radiation means subatomic particles that are released from unstable atoms with a certain amount of kinetic energy. So it's kind of like a different kind of thing. We're going to treat these particles as if they were radiation also. And the one that is of most concern to us, perhaps from the point of view of health, is ionizing radiation. So this would be radiation of either type, electromagnetic or particulate, that can produce charged particles in matter. Now, for those of you who like it, we're going to continue doing here some more definitions. I'm sorry, these are things you could probably look up on your own, but we're going to include them in here just to give us a kind of like a good menu or a good repertoire of terminology here. So when we say radioactivity, we mean the spontaneous emission of electromagnetic or other types of radiation. So radioactivity means spontaneous radiation. Radioactive isotopes are unstable atoms that give off excess matter or energy or both as ionizing radiation. We sometimes call this process radioactive decay. So understand, not every isotope of an element is radioactive, only those that are unstable. When you have this type of radioactive decay, we say that the parent nuclide is the nucleus that is undergoing the radioactive decay, and the daughter nuclide is the new nucleus that is made. They're sort of parallel to the reactant and the products in a standard chemical reaction. Also, for those of you who are interested, we're going to look at a few bits of history here. This is Wilhelm Röntgen, and in 1895, Röntgen discovered X-rays. He essentially discovered that a photosensitive paper across the room, or kind of not across the room, but a distance from a power source, would basically be activated. And because they didn't know what it was, they called them X-rays. Of course, this was later on developed, and this is Antoine Becquerel, who in 1896 discovered the radioactivity of uranium. Now, he had basically learned of Röntgen's discovery, right? So he got interested. He began to look for a connection between another phenomenon he had found, which was a phosphorescence in certain materials. And then he connected that with the newly discovered X-rays of Röntgen, and thought that these phosphorescent materials, such as in some uranium salts, what they might be doing is emitting these penetrating X-ray like radiation. And so by about 1896 or so, he basically did some experiments, and he arrived at the explanation that the radiation came from the uranium itself. It did not have to be elicited from an outside source. It was kind of like innate in these uranium isotopes. Of course, a very famous person, Marie Curie. In 1898, she discovered polonium and radium, and of course, she is one of the pioneers of nuclear chemistry. She was the first woman to win a Nobel Prize. She was the first person and the only woman to win 2 Nobel Prizes, and the only person to win a Nobel Prize in 2 different sciences. Sadly, she died in 1934 at the age of 66 from cancer that was due to exposure to radiation in the course of her scientific research. I don't know if this is true or not, but I heard from somebody that was doing a lecture that I attended that she used to carry around in her, with her, tubes with radium, with radioactive radium. So that may have been the reason for the cancer. Now, as time went on and the technology was developed, we were able to identify that there were different kinds of rays or different kinds of radiation emitted by these so-called radioactive isotopes or radioactive elements. So if you put a radioactive substance such as uranium in a dense metal block like lead, which shields most of the radiation, so that you can essentially allow it to exit from just one single opening on one side, and then you take that radiation and you subject it to an electrical field, you find out that on the photographic plate on the other side, you detect three different spots. One of them stays in the middle, one of them moves upward towards where the negative side of the electrical field would have been, and another one moves to the bottom towards where the positive side of the electrical field would have been, indicating that the ones moving up, which were called alpha, must have had a positive charge. The ones moving towards the positive end of the electrical field are called beta, and they must have a negative charge. And then the ones that were not affected by the electrical field must have not had a charge. It was later on found out that these were not particles. They are actually electromagnetic radiation called gamma rays. Okay, so this is, again, the type of symbols that we used to represent isotopes in Chem 1A. So in order to describe these nuclear particles, these different nuclides and nucleons, we're going to use the same symbol, maybe tweak a little bit the meaning of these different numbers. Okay, so let's start with a proton. Notice the way we're writing it. We're writing it with the letter P, and on the left, a superscript of 1 and a subscript of 1. So essentially, we're going to say that a proton has a quote-unquote mass number of 1, and quote-unquote an atomic number, which we sometimes refer to as an atomic charge of 1. And hence, the symbol we're going to use to represent protons. To represent neutrons, we're going to use the letter N, and notice that, once more, the quote-unquote mass number, which is protons plus neutrons, be 0 plus 1, so that'll be a mass number of 1, and the atomic number or atomic charge or nuclear charge would be 0, because neutrons don't have a charge in them and they're not protons. Okay, so let's represent now electrons. And we have two different ways we can choose to represent them. We can use the letter E, or if we're representing the emission of the so-called beta particles that I described on the previous slide, we can use the Greek letter beta. Notice again the symbols on the left. Mass number would be 0 because there's no protons and no neutrons in an electron. And the quote-unquote atomic number, right, or atomic charge, we would call it -1 because that is the charge of an electron. And essentially, a beta particle is an electron. We'll talk a little bit about the difference in a moment. Actually, let's go ahead and talk about it now. So remember, in chemistry, we learned that electrons are the part of the atom, the subatomic particles that exist outside the nucleus and whose properties are described by wave functions, right? By orbitals. And we know they have a -1 charge and such. Now, when we use these symbols here in nuclear chemistry, we're going to be referring to electrons or particles that, although they are physically electrons, we are talking about particles that are emitted from an event that happens in the nucleus, not in the orbitals of the atom. Okay, so hopefully that gives you a bit of an explanation of the difference between what we talk about when we talk about electrons or beta particles in nuclear chemistry versus electrons in regular chemistry. Now, one of the interesting particles that we find in these events is something called a positron. Notice that this is also an electron, but it belongs to the class that we call antimatter. So also, again, we have a mass number of 0, but in this case, although this particle is kind of physically like an electron, it carries a +1 charge. The last type of particle we're going to consider, these are not the only ones, but the most common ones, is called the alpha particle. We said it has a net positive charge. Notice the mass number here is 4, and the atomic number is Z equals 2. That means that you have 2 protons and 2 neutrons. In other words, an alpha particle is essentially a nucleus of a helium-4 atom. That's essentially what an alpha particle is. And so sometimes we represent it as the symbol for helium, He. Sometimes we use the Greek letter alpha to describe it. Now, why are some isotopes radioactive and others are not? This is a very interesting graph, and we'll come back to it later on. So remember, think about the nucleus. You are essentially putting together in a very, very small space all these positively charged protons and all these non-charged neutrons. Now, protons are positively charged. They're crammed into a small space, and therefore you would expect a huge amount of repulsion between those positive charges. Now, this is not the only force that's in there. There are other forces between neutrons and between neutrons and protons. And so the particles in the nucleus are held together by a very strong attractive force that is called the nuclear strong force, or the strong nuclear force, which acts only over very short distances. Now, the neutrons will contribute to that strong nuclear force, but because they don't have charges, they don't repel each other like protons do. So since you have these two forces at play against each other, the repulsion of protons and the strong nuclear force, that's a force of attraction, you would think, therefore, on a first approach, that the stability of the nucleus will likely depend on the ratio of neutrons to protons. And so we start out by measuring for different types of elements here on the bottom. In other words, number of protons is the atomic number, which is the identity of the element. And then what we do is we look at all the various isotopes of each one of those elements, and we calculate here on the y-axis the number of neutrons. So notice that for every single element, there is more than one isotope. In other words, there's more than one nuclide. And then what you do is we're going to graph in here which of those isotopes are actually stable. In other words, which isotopes of these elements are known not to undergo radioactive decay. Now, for small atoms, it seems like a 1-to-1 ratio will do it. You can look here at the first part of this graph, and you can see that for the first 20 or so elements, a ratio of 1-to-1, 5-to-5, 10-to-10, 20-to-20 neutrons to protons keeps everything fairly stable. This is the line that represents a ratio of 1-to-1 of neutrons versus protons. But notice that right around that atomic number 20, above that, notice that now the stable isotopes actually fall in a range where the ratio of neutrons to protons is larger than 1. In other words, you seem to have more neutrons than protons in order to get stable isotopes. So as the number of protons increases, and therefore the proton-proton repulsion increases, you need a slightly higher neutron to proton ratio in order to maintain stability. And so what it generates is this area here that you can see shaded in, and we call it either the belt of stability or the valley of stability. And we'll come back to this graph later on to explain why the different types of decay, beta, particle, positron, alpha particles. Okay, feel free to pause the video at any time just so you can kind of gather all this and make sure you understand it. Very quickly here, as we go through these, there's some patterns that emerge, and we're not going to go in detail over these. But for example, it seems like certain numbers of neutrons and protons are extra stable. Uh, for example, it seems like numbers of neutrons or protons like 2, 8, 20, 50, 82, 126, atoms that have those type of numbers seem to be stable. It's kind of similar to when we studied the elements on the periodic table and found that certain elements who had like a certain quote unquote magic number of electrons were more stable, the noble gases, right? 2, 10, 18, 36. So this is something similar, kind of like a magic number. Another pattern that we find is that nuclei that have even numbers of both protons and neutrons are typically more stable than those with odd numbers of neutrons and or protons. And one more thing is that all isotopes of the elements with atomic numbers higher than 83 are radioactive. So kind of like atomic number 82 is kind of like the boundary of stability. You can see this on the following table, which you may have a form of this table in your textbook. And what is important here is look at the third column here. It tells what are the number of stable nuclides for each of the known isotopes. And what you see is that for those nuclides that have an even number of protons and an even number of neutrons, there are 168. In other words, more than half of the known stable nuclides belong to this category of atoms that have even number of protons and even number of neutrons. Okay, so now we know what are the types of particles that we are going to be dealing with. So when you have a nuclear decay event, we're going to call it a nuclear reaction, we can also write nuclear equations similar to the chemical equations we wrote in Chem 1A to describe chemical reactions. So here are the rules. Number one, when you write a nuclear equation, you have to conserve the mass number. Okay, so in other words, the sum of protons plus neutrons in the daughter nuclides must equal the sum of protons plus neutrons in the parent nuclides. So let me show you a typical nuclear equation. There you go. So we start with uranium-235 reacting with, you can understand that as being a symbol for a neutron, right? We've seen this before already. So that's a neutron. And here are the products. But remember, in this case, we call these the daughter nuclides. Now, to apply this rule, we're going to look across the top. In other words, the sum of the numbers across the top, the A values, has to be equal. So on the left, we would have 235 plus 1. And on the right, we would have 138 plus 96 plus 2 times the value of 1 for a neutron. And by the way, in these types of situations, no, we don't cancel out the neutrons on the left side with the neutrons on the right side because they may have different sources. Okay, so you can see where the values of A equal on both sides. The second rule is we have to conserve the atomic number, Z, or sometimes called the nuclear charge. So the sum of the nuclear charges in the daughter nuclides must equal the sum of the nuclear charges in the parent nuclides. So let's look at this equation again. And this time we're going to look at the numbers on the bottom. So for the left side, for the parent nuclide, we have 92 plus 0. And for the daughter nuclides, we have 55 plus 37 plus 2 times 0. Remember, we're adding the values across the bottom. Excuse me. So that's it. That's as simple as it gets. So let's do a little practice here. It says here that that symbol, PO212, remember, because the atomic number is unique for every element, we don't have to write it in all the time because it's somewhat redundant. So how do we say this? Remember, well, we say this as PO212, or if we look at the actual element, we find that it is polonium, right? So just notice what I said, that you can write that also. Let me see if I can make my pen work here. We can say this as polonium dash 212, and so we would say it polonium 212, or for short PO212. All right, so let's start out by saying kind of like looking at what it says. It says it decays by alpha emission. We're going to write the balanced nuclear equation. So what is alpha emission? It means that it releases an alpha particle. So an alpha particle, we can write it either as a nucleus of helium, or alpha with a mass number of 4 and a nuclear charge or atomic number of 2. Now we need to find out what is this polonium guy, because in order to balance the nuclear equation, we need to know both its mass number and its atomic number. So we go to our good friend, the periodic table. We're going to find PO, polonium. Oh, there it is. There's polonium, and it says that it's atomic number 84. Notice that the average atomic mass of polonium is 209. And we have here one that's 212, right? Just take those kind of things into account. Okay, let's go back to our problem here. And let's say that we're now going to write this in the following form. Remember, polonium 212 has an atomic number of 84, and the reaction produces an alpha particle and some daughter nuclide that we're going to have to figure out what it is. So this is our unknown. So in this case, in balancing a nuclear equation, we don't know necessarily what the daughter nuclide is, and the process essentially consists of figuring out who the daughter nuclide is. So let's apply the rules. Rule number 1 is that the mass numbers have to be the same. So on the left, we have 212, and on the right, we have 4 from the beta particle, from the alpha particle, plus A. So algebra says that A equals 208. Now let's find out what is Z. So once more, the numbers across the bottom, the atomic numbers, have to be the same. So on the left, we have 84. On the right, we have 2 plus Z. So algebra tells us that Z equals 82. So what we had to do now is go back to the periodic table and find out, well, what is the element that has an atomic number 82? I'll let you guys do that if you want. Yeah, that's right. It's lead. And so to complete our balanced nuclear equation, we put in lead 208. Notice where the numbers go. And that is the identity of our daughter nuclide here. You can pause the video if you want to go back again to your periodic table and check, make sure that was correct. Okay, and let's close out this brief section by comparing chemical and nuclear reactions. We studied chemical reactions in Chem 1A. Don't worry, we're going to continue studying. Don't worry, we're not done yet. And we are studying nuclear reactions now. Okay, look at the comparison. In chemical reactions, atoms are rearranged by the breaking and forming of chemical bonds. Whereas in nuclear reactions, elements are essentially converted from one to another. Notice in this reaction, we changed polonium into lead. Remember that in chemical reactions, one of the ideas of balancing equations is that you have the same kinds of atoms on both sides of the equation. Number two, in chemical reactions, only the electrons in orbitals are involved in the breaking of forming of bonds. In other words, chemical reactions essentially involve electrons in the orbitals. And most of the time, they involve only electrons in the valence orbitals. In nuclear reactions, you're going to have protons, neutrons, electrons, and even other kinds of elementary particles involved in the process. Number three, chemical reactions are typically accompanied by the absorption and release of relatively small amounts of energy. I mean, think about the more violent reactions we can study in a lab. We're talking combustion reactions. You're talking a few, 1,000 kilojoules per mole of energy. Reactions of the nuclear kind are accompanied by the absorption or release of tremendous amounts of energy. I mean, millions of kilojoules per mole. We'll study that later on. And number four, chemical reactions, as we saw in the previous unit of kinetics, are influenced, the rate of those reactions is influenced by temperature, pressure, concentration, and the presence of catalysts. This is all in accordance with the collision theory model that we proposed. Nuclear reactions, on the other hand, are not normally affected by temperature, pressure, or the presence of catalysts. All right? Okay, so this is an introduction up to now. Our next step then is to find out, well, what is the nature of this nuclear stability and instability, and what is the nature of radioactive decay?